Well, greetings folks. Today we're here to talk about calorimetry. Calorimetry is a method of measuring heat flow, and whether something gains heat or loses heat can be determined through the process of calorimetry. Make sure that you have a notebook, pencil, and a calculator handy for today. We'll start with the word calorimetry, which actually comes from the word calorie, which is a measurement of heat energy in the English system, which of course is 1 calorie is 4.184 joules. So it's a unit of measure as well. But this is a process that you use. And in calorimetry, what we want to do is we want to be able to measure the amount of heat that it takes to change the temperature of some stuff. And depending on what that stuff is, the temperature will go up a certain amount based on how much heat you put in. So how much will it go up? Well, it depends on the stuff. The change in temperature is symbolized many times by a triangle and then a capital T, and the triangle means change. So change in temperature is quantified by something called the heat capacity of the substance. And the heat capacity of the stuff or the substance is the amount of joules it takes to raise that substance 1 Kelvin or 1 Celsius. And the distance of 1 Kelvin or 1 degree Celsius is the same, and so K or C, when you're talking about changing a quantity of temperature, can be used interchangeably. Well, there are two widely used measurements of heat capacity for substances. One is called molar heat capacity, and molar heat capacity is the amount of joules or energy needed to raise 1 mole of a substance 1 Kelvin. 1 mole of the substance 1 Kelvin. You can see that there's a 1 mole down here. That's the molar heat capacity of something. The other way that heat capacity is measured is in something called specific heat capacity. And specific heat capacity is the amount of energy measured in joules needed to raise 1 degree Celsius of 1 gram of a substance. So the units on here are joules per gram Kelvin or joules per gram Celsius. This is symbolized by the letter C with a small p below it, meaning heat capacity. Now, if you're in the 13th edition of the textbook, there's a table on page 182 that gives a number of specific heat capacities for substances. And I have a website right here that has specific heats and molar heat capacities for a lot of things. You can see aluminum has a specific heat capacity of about 0.9 joules per gram degree Celsius, giving a molar heat capacity of about 24. Water has a really high specific heat capacity, 4.186 or 4.184 is what you'll find in your textbook, joules per gram degrees Celsius. You'll notice that on the website this is at 20 degrees Celsius, whereas your book many times will use 25 degrees Celsius as its standard. That's why the difference in thousandths right there. Iron and many metals are under a half a joule per gram degrees Celsius. You can see brass is 0.38, zinc is like 0.387, and then you can look at some other ones like copper and gold and lead as well, all fairly small specific heat capacities. So the higher the specific heat capacity, the more energy that's needed to raise its temperature. And so you can remember this pretty easily if you think on a hot summer day when you're by the lake. Even though it's 90 degrees outside, the water in the lake isn't going to be 90 degrees because it takes a lot of energy to raise that water a degree Celsius or a 1 Kelvin. Whereas conversely, if you have some things made out of metal, like let's say you're at a playground next to a lake, the playground equipment, usually made out of iron or some type of metal, that could be super hot to the touch. That's because even though the same amount of heat is given to the water and the same amount of heat is given to the iron, it doesn't take nearly as much heat to raise the temperature of the iron as it does to raise the temperature of the water. So here's an equation to relate specific heat capacity to a calculation. And specific heat capacity is equal to the amount of heat Heat is usually symbolized by the letter Q, but remember, heat at constant pressure is also known as enthalpy and is symbolized by delta H. And for now, we can use those interchangeably as long as we know it's heat at constant pressure. M stands for mass, and mass has to be measured in grams. Oh, I forgot to tell you that heat energy is almost always measured in joules here. And then this is triangle T, which is always temperature final minus temperature initial. And as long as it's in either Celsius or Kelvin, as long as they're the same units in Celsius or Kelvin, they're absolutely fine because you're looking at the change in temperature. And this is specific heat capacity, of course, measured in joules per gram degrees Celsius or joules per gram Kelvin, and the units are interchangeable. We can rearrange this equation to solve for the energy, and so Q, or energy, is equal to MC delta T. MC delta T right here. So if you know three of these variables, you can find the fourth variable. So one common lab method of calculating one of these variables right here is a calorimetry, or using a calorimeter lab method. A real common classroom calorimeter is a styrofoam cup. And you can see a picture on my paper right here, and also on this website, that they'll have some water or a liquid inside. And then there'll be a thermometer to measure the initial and the final temperature. The styrofoam cup, or cups, are usually used because they're good insulators. They don't allow the heat to escape anywhere else except to go into the thermometer. And then there's usually a method of stirring it as well. One real common use of a calorimeter is to find the specific heat of an unknown substance. And when you do that, you find out how the transfer of the substance to water's heat can be calculated. So let's say we had some stuff, let's say it's a piece of metal, and we knew its temperature and we knew its mass, and we heated it up, maybe in some boiling water, and we knew that it started at boiling water's temperature, which might be pretty close to 100 degrees Celsius. Then if we take that substance and dump it into our styrofoam cup with a known mass of water and at a known temperature, now, since we know the specific heat capacity of water, we could find the specific heat capacity of the unknown substance, because the heat lost by the stuff is equal to the heat gained by the water, as long as we can have it insulated good enough to not lose a lot of that heat to the surroundings. So there are other types of calorimeters right here as well. These are called bomb calorimeters. They work at a close to constant pressure, but not always. And if you just Google calorimetry, you can see lots of different methods of using Q equals MC delta T to find different variables from the equation. So here are two example problems of doing some calculations. First of all, calculate the heat needed to raise 250 grams of water from 22 degrees Celsius to 98 degrees Celsius. So step number one, organize your data, and organize it in terms of Q, M, C, and triangle T. So make a little table over here to organize what you know. The thing that we want to know is heat, so we don't know Q, or we don't know our enthalpy or our H, as long as it's a constant pressure. We know our mass is 250 grams of the water. We know the specific heat capacity of water is 4.184 joules per gram degrees Celsius. And we know that our change in temperature, always calculated by temperature final minus temperature initial, is 98 minus 22, or 76 Celsius or 76 Kelvin, because remember the Celsius and Kelvin can be used interchangeably when they're a change. And so let's put this into our equation. Q equals M times C times delta T. And then when you multiply those together, go ahead and pause now and try it on your calculator. All right, hopefully you got about 7.9 times 10 to the fourth joules. 7.9 times 10 to the fourth joules. Second example problem. This time we have a bed of rocks, a bunch of rocks that are sitting outside, and we want to find out the change in temperature of these rocks. The rocks were known to have a specific heat capacity of 0.84 joules per gram degrees Celsius, and we have 50 kilograms of these rocks. And we know that they're going to absorb 450 kilojoules of heat from some source. So, once again, our equation we're going to use is mc delta T, and this time we're looking for delta T. So we know the other three items, but we're going to look for triangle T. And so we can plug these into the equation where Q is 450 times 10 to the third joules. Notice it said kilojoules right here. I converted it to joules because our specific heat capacity is in joules. Times the mass, and I converted the mass to grams, so 50 times 10 to the third grams. This was in kilograms, and I converted it to grams. The specific heat capacity was given to me in the problem. It's 0.84 joules per gram degrees Celsius, and I want to find the triangle T. Try that on your calculator right now and see if you can solve for triangle T. All right, hopefully you got about 10.7 degrees Celsius or 10.7 Kelvin, and that's our change in temperature for these rocks. All right, to end today, I have a short little video for you that I'm going to embed in this right now, and it happens to be a music video, and it has a lot to do with M and C and delta T. So I'll go full screen on this guy right here, and please enjoy.
Working at my lab bench, late one night you see, I got to make reactions for my class of chemistry. Just right then my beaker began to get real hot. I stuck in a big sensor and said, hey, what you got? The temperature kept rising and I began to fret. I don't want my experiment to explode and get me wet. So I looked up this reaction to see what made it sick. Turns out that it is right okay, cause it's exothermic. Energy in parts gets lost and sent out to the free. Turns out this puppy got lost in potential energy. So how will I ever calculate this quantity called Q? Here is the equation, and I leave it up to you. MC delta T. I said MC delta T. MC delta T. Oh, that's calorimetry, y'all. That's right, dog. So I put it in some water, whose mass I sure did know, and plugged it in for M, and said, now there you go. Water has this real neat thing that's called specific heat. It's 4.18 joules per gram. Hey man, that's really sweet. It tells you how fast it heats up when someone gives it juice. It's constant, and maybe it's called C, sure to keep it loose. The temperature kept rising from beginning to the end. So I worked out the difference. That's delta T, my friend. When I plugged the numbers in, I got some happening joules. I tell you, this calorimetry is monkey funky cool. So from now on, when you or me has reason to calculate, just check out this equation. There ain't no need to wait. It's an MC delta T, MC delta T, MC delta T.